Okay. It records to the cloud. When it gets done, it don't take this company very long to post that video, well, to tell me it's ready. And then I'll download it to an external hard drive, and I'll also, I put a link to it in Moodle so that you can click it. Whoever misses can click it and see it with the Zoom company. So anyway, so whoever's watching and recording, this is ELC 117, and it's April 28th, Tuesday night, and we're going to be covering chapter 37 on motors. So, and as you see the trees in the background, I'm out here in my carport because I've got 3-phase motors in the back of the truck and stuff that we're going to do for testing tonight. So instead of taking the stuff in the house, I'm just tailgating it out here. Okay, so I'm going to set up a screen share, and we're going to start out. If you got your book, okay, and we'll pull up right there, and current slide. So do y'all see the PowerPoint now?
Yeah.
And you're probably seeing some little camera screens on the right side of my screen, or not.
Yeah.
Okay. So now let me grab my book here. Now tonight it's 37, but Thursday night we're going to back up to 36 on VFD. So I'm making good and sure that we go ahead and cover motors tonight, and I never like waiting till the last night to try to cover motors, because if somebody happens to miss that last night, you know, it would be unlikely that they would even go back and try to see it. So motor installation, and let me actually get my screens over further. That's better right there now. So we're going to look at how to determine the full load current rating of different types of motors using a National Electric Code. The code book is about that thick, as you remember seeing it at school, that one I had. But the good thing is you don't particularly have to buy one unless you're getting ready to study for a state test. You can get free access on your phone or your computer from NFPA, the people that write the code book, National Fire Protection Association. You can go on the NFPA website and give them a little bit of information about yourself. You'll set a profile up, and they'll let you have access to all the code books, electric code books, fire alarm code books. There may be even hundreds of code books. There could be. There's so many of them on there that I never thought, I would have never dreamed there had been that many code books in the U.S., but the NFPA produces lots of code books for different things. So, okay. So we're going to look at how do you look up the full load current rating of different motors? How do you determine the wire size or the conductor size for a motor? And how do you determine the overload size? Like if you see my webcam, the overload relay up under the contactor, how do you actually know what to set that to? So that's going to be something we're going to be looking at. We'll look at how do you size your short circuit protection devices that actually go ahead of the starter. So with your starter, you know, you have the overload relay under it that's going to protect the motor. And then above it, you're going to have either fuses up there or circuit breakers that actually feed the motor, that feed the starter. And that's going to be what they call your short circuit protective device. That's going to be something upstream from that starter. And we're going to look at that. And then how do you know what size starter to even have to begin with for a particular motor? And there's charts for all this stuff that's in this chapter, and it makes it real straightforward to know, you know, If I go order a starter, how do I know what size to get and all? And that's real straightforward stuff there. So we're going to go over that. Okay, your nameplate data, which is standardized by NEMA. NEMA in the U.S. is the National Electrical Manufacturers Association, and they have standards that a lot of companies agree to stick with. So there is some kind of standardization in the U.S. on data that's on nameplates for motors. And I'm going to move the webcam just for a second over to this motor right here. And do you see that nameplate there in my webcam? Do y'all see that motor I'm looking at?
Yep.
So this is a motor here. It's a 3-phase motor I've got here in the back of this truck I'm tailgating with, and it's a Ball-Door brand, Ball-Door Reliance wash down duty motor. You could wet it, you could spray it down, like in a farm or food processing, and it's got a lot of information on there. So all that stuff like horsepower and volts and amps and all that good stuff. We're going to look at all the different things that are on there that you need to know when you're dealing with motors. And that nameplate can also help you pick a replacement motor. If you couldn't get a Ball-Door, if you had to go with a Leeson or some other brand, then if you have enough information off of that nameplate, and you could actually get a motor that would replace it of some other brand, and it would bolt right on and do the same exact job with the same shaft size, the same height from the base of the shaft, the same mounting, like the mounting down here, the foot mount or face mount, however it's mounting. The information on that nameplate is going to tell you everything about that motor. It gives you information that it would give you partial information about the dimensions, well, actually the mounting of it, for instance, and then the shaft size and height and all that, plus all your electrical data, your volts and amps and all that good stuff. And we're going to look at all that. So information that's on the nameplate, it consists of this. There's a lot of stuff that's on that plate. Your manufacturer's name, your horsepower rating, your RPM, that's your revolutions per minute, the frequency that it accepts from the power line or from a VFD, and how many phases does it have? Is it single phase? Is it 2-phase, or is it 3-phase? And then the motor type, what the construction of the motor internally. Is it a squirrel cage type motor internally on the windings, or is it a synchronous motor? Is it a wound rotor motor? When you're getting at the physical details of how the windings are made, then you're talking the type of motor. And there's a lot of motors is a world of its own, as you'll begin to see. So also on that same nameplate, you have the hey McGill, how you doing?
Hey, how are you?
Pretty good, man. About yourself?
Good, good.
Glad you made it. Be jot down. Everybody just seeing. We got Hunter, Jamie, got McGill, Patrick, Jameson. Okay, 1, 2, 3, 4, 5. That's good. Off to a good start here.
Durwell,
Okay.
what chapter is this in the book?
In the book,
Yeah.
chapter 37, page 356.
Okay. Thanks.
I'm in Durwood.
Victor,
Dylan.
hey, how you doing?
Hey, I'm good.
All right. We just got started.
All right, that's good then.
We're in the book. We're on page 356. If you got your book, if you want to be kind of scanning through,
Yes, sir.
because there are certain things just in the book that the PowerPoint don't have everything in it, even though I'm going to hit the high spots.
Uh-huh.
The PowerPoint, there's no way for it to have every little detail. So I'll mention some things I'll read directly from the book that it's not in there. So, okay, so that motor data plate, this on all your motors. It also has the frame size on there, and we're going to look at that. The voltage, full load current, enclosure type, duty cycle, temperature rise, service factor, locked rotor code letter, NEMA design code, efficiency, installation class, model, serial number, and connection diagrams. That's a lot of information, but seriously, when you take a glimpse at that motor, look at all the information that's on there. I mean, everything that I just mentioned is all right there. And then your connection diagram is right there inside the CAD head, what we call the CAD head, where your wires are. There goes your connection diagram. So whether you go low voltage 230 or high voltage 460 to 480, it gives you that. And we're going to go over how do you physically wire either way. We're going to look at that. Okay. So this is a picture of an example of a nameplate that has a lot of this information on there. And they focus, the first thing they'll highlight is HP, that's horsepower. So that's a 1 horse. Of course, they go way higher. I've seen them as high as 150 horse, and they go even bigger than that. So these are standard horsepower ratings that you can buy motors off the shelf. Starts out, there are fractional horsepower that go less than 1 horse, but this is just showing, in whole numbers, integral type horsepower of whole numbers. So it starts out at 1 and it goes up to 4,000 horsepower. That'd be a whopper of a motor. At Smithfield, what's the biggest size that you guys have, McGill and Victor?
The
that
highest
you're
I've
aware
seen
of?
is probably
How much?
50.
50 horse. Yep. We had 150 horse on an air compressor outside, and it was so big I couldn't even wrap my arms around it. It was pretty big, and it ran a big Sullair screw compressor for the whole plant. It was one compressor that ran the whole plant. So it was a whopper, and it drawed about 165 amps per leg. You put an amp clamp around the legs, it's about 165 amps per leg. It was a lot. So, wires about that big around, pretty big. Patrick, how about where you're at? What's the largest motor that you know of?
150 horses on our compressors. We have 100 horse and 250 horse compressors. Yep.
Sounds right. So there goes the standard off the shelf horsepower size is there. And next part of your nameplate would be the RPM. That's going to be how many revolutions per minute that it'll turn. So in the range of 1720 is typical, but sometimes you'll see a 3450 like on blowers. So if you got a blower motor for an air blower, it may be double that. So, but most of them for production equipment are usually around in 1720, 1725, somewhere in that range. Or so close to it. The HZ is for hertz. Hertz is that's the unit for frequency. So that tells you the frequency that it'll accept coming into the motor from the power line or from a VFD. So whatever's running it, if it's straight power line of a motor starter or drive, 60 hertz is the rating on that motor there. And if it's something a motor's being used in other countries, in Europe, then it will be 50 hertz because their power plants, they run 50 hertz, not 60. Phase is going to tell you, well, how many phases does the motor have? Is it single phase, 2 phase, or 3 phase? And that's how many hot wires do you have? For a 3-phase motor, there's 3 hot legs, and actually, for single phase, you have 2 hot legs. It can be if it's a single phase high voltage. So if you got a single phase motor, in all cases, it's going to be two current carrying conductors going to the motor that carry current. If it's a single phase motor going on 120, it's got a hot and a neutral that carry current to and from the motor. If the single phase motor runs on, say, 240, it's got two hots, a L1 and a L2, and they're both hot, but they're different phases. So it's still two current carriers to the motor if it's single phase. And then there's some odd motors that are called two phase, and they're going to show those in this chapter. Those have two hots and a neutral. And so it's two hot wires and a neutral. But I've never seen a two phase in person. They just show them in the book, but they're not common. And then the type of construction of the motor inside, you're talking, when you look at the guts of the motor, how are the windings constructed? Is it an induction motor, or is it a synchronous motor or a wound rotor? There are different constructions of motors. The frame size, there's a lot of frame sizes. And for instance, the one that I have here, this frame size says 56C. I don't know if you can read. Can you read that?
Yeah.
It's a 56C. So what that includes is this. That information, it entails the mounting type. It entails the height of the shaft from the base to the shaft. It entails that stuff it all has to do with that. So there's a chart that we're going to look at that would take that 56C number and break it down and tell you dimensional information about that motor. So again, if you had to replace it, but you didn't have a ball door, your supplier didn't have a ball door, he says, I've got leasing. Do you want to leasing? And you say, well, if it's got a 56C frame, and if it has 234/60 voltage, if it's a 3/4 horse motor, and if it's a 1750 RPM, basically that information right in there, those five pieces of information right there, if you match that with any other brand motor, then you're fine. You'll run, because these are standardized things that are by NEMA. So NEMA, all of the companies, the U.S. companies, they agree to use standardized frame numbers that represent dimensional data about the motor and all. So, again, you can order. You're not stuck with one brand. You're not stuck with one brand motor. So that's not a problem.
Does that also include the shaft size, or are they going to vary?
It's going to include. Let me fast forward. Now I'm going to verify that. It includes that. Let me go forward. This is a reference chart. Let's see. That's an IEC. Let's go. This is the NEMA chart. Now let's just zoom in on that. That's in your book on page. Excuse me. Page 361 in your book. Now, let me zoom way on in on that. Let's see. And let's go. Move the cameras over. I tell you what, man, I like this zoom. This zoom is a lot better. I like it. It's got it's fast. It ain't sluggish. And when you hit a button to do something, it's not a maybe. It'll go ahead and do it. The blue button was kind of maybe. Maybe it do what you want to do. Okay, now to answer your question, Jamie, the answer is yes, because look, for instance, if you have a 56H, can y'all see that chart pretty good?
Yeah.
Now, for instance, if it's a NEMA, if you notice up top, it says a NEMA frame size. So if it's a NEMA frame size, if it's a 56 frame, Then dimension D, now you got to go look at that blueprint up there. And dimension D, if you find that in there, let me go larger. You got to get way in to be able to read oh, that's too far. Okay, so let me try to read in my book. In D, that's P. There's a dimension C, BA, P, D. Okay, D, dimension D is from the base of it, from the floor to the center of the shaft. So if you look, where's it at? Hold on, I just had it. I just had it and lost it that quick. Hold on. Writing is so small. That's funny how you find something, turn your head, and you lose it. Give me just a minute here. Dimension D is, and I got to find it on the blueprint so I can point to it again. I just had it. That's BD. Where is, that's O.
You're right at your corner right now.
That's actually BD. So you got a
right to the right of
BD. See here, there's to the right. Okay, right there. Yeah, that's it. Or is that O?
I think that's D.
No, it's actually D. D right down here. This is it right here. Yeah. So D gives you from the center point on the shaft to the foot. Now I mean, so D would be, if it's a 56, it'd be 3.5 inches and so on. How about shaft diameter? So let's see if we can find that. It would be a small number, like, let's see, maybe AA. Where is AA at? The smallest dimension I see on those rows is AA, and let's see where AA is. See if anybody can find a double A reference point in the drawing.
It's on the drawing on the far right.
A double A. Okay, let's go over.
But I don't see what.
No. I'm just looking for shaft size to see. I'm thinking that the shaft size would be involved with it, but I'm just trying to remember where is it? Okay, NEMA shaft is U. So U would give you the shaft size right up there. You see that?
So that's a 5/8 shaft.
Right. So U is right over here.
Mm-hmm.
Right. So U is right over there. And so if we go down to the chart, I knew it was. I just had to find it. So your shaft size would be under U for whichever motor it is. And so if it's a 56 frame size, then it has a 5/8 shaft. If it's a 143T, the motor here in the back of my truck is a 56C. Okay, that's a 56H. But you see that this one piece of information here, the NEMA frame size, it encompasses every dimensional aspect of the motor, so that you can go to some other brand and say, your supplier says, I got this other brand. Can we sub it? And you can say, as long as it's got a 56C frame and the voltage matches, the hertz matches, horsepower matches, and the RPM matches. And that's basically it. The rest of it, and then, well, there is more. The temperature rating on the motor, and there is more stuff we're getting ready to get into right now, because I can tell you, if you got a motor on top of an oven, you got an oven running, you got an exhaust fan on top of that motor, on top of that oven, you better have a motor that can handle that temperature, or it ain't going to last. Because where I used to work at, we had some penny pinchers in the office that didn't want to pay for an oven duty motor. So they would order, they say, no, we're going to get one from, just a standard motor. We say, okay, sure. Okay. You get you when you're going to keep buying them, So that's what kept happening. And then they finally found out you had to have the windings in the motor. They had to be high temperature rated, or you were never going to last. So, had to buy a couple of motors before they really had to accept that. So,
those guys work at Schindler now.
I wonder where did they get to, They say, oh, we can't afford that. Oh, I can't afford that. Oh, yeah, okay. So, sure, okay. All right. Have it your way. You'll be buying more of them. It costs you more in the long run to not get the right thing, because you just keep buying, So, but anyway, as you see, basically you've got a whole blueprint of data that's represented by a frame size. Does that make sense?
Yeah.
Yeah. All of that data that runs that whole column, that whole row of information is represented by a simple frame size that's on that data plate. So it's a good, and the chart that you're looking at is a United States NEMA standardized chart. But if you got motors that come from overseas, let's back up and look. Let's see. Let me go back to full screen. Now, if I back up one, it says IEC. So the IEC is International Electrotechnical Commission, and they're based out of is it Netherlands or somewhere over there in Europe? It's a European. I forget what it is but and it may be even Belgium. It may be Brussels or somewhere over there, but it's Europe. So the IEC are metric. They're metric designations. So any equipment you get from overseas is going to have IEC rated motors, and the frame sizes and all that stuff. It's a whole different rating system, but it's still dimensional. So if you take a look at the IEC chart, it's the same idea that a frame size would represent a whole set of blueprints will be represented by one particular code on the nameplate. And the IEC frame numbers would be in the left column there. You have the 63, 71, 80, 90, and so on. And those numbers are going to be, I'm sure they're in millimeters, and I want to see a reference. It may be in let's see, where does it tell you?
Millimeters.
Yeah, I'm just wondering what is the red and what is the black?
Inch dimensions are red and metric or black.
Okay, that's what I thought. So it's got both. So in metric, it's in millimeters, and then you got 3.9 inches would be 100 millimeters. Okay. So you got it whichever way you're going there, but McGill and Victor, you got IEC and you got NEMA out there at the plant, don't you?
As far as I know,
Yeah.
we just got the NEMA.
Okay.
They might have some on the other side. As far as our area, we just got NEMA. The only things we usually deal with is the 143 TC.
Yep.
Or the 143 or the 56C or the 56. That's all we
Right.
really deal with.
Those numbers they sound familiar from where I was at. They're real common frame sizes and all. But how about your stuff, your machines that come from overseas? When you order machines from overseas, you probably got, well, you may have, I would think you would have IEC on anything you buy from Germany or anywhere.
Well, those machines been sitting there a little while, so they probably got NEMA motors in them now. I mean, they probably changed that.
Exactly. They change them out when they go bad. That you're exactly right. Yep.
Yeah.
Right. Because that makes perfect sense.
So like you said a while ago, as long as the frame fits and the motor size and the horsepower and all that fits, then they're gonna put it on.
That's right.
I got
Exactly.
something going.
Exactly right.
I got something going.
I hear Thomas. Hey, Thomas, how you doing, man?
All right, how you doing?
We're hanging. I'm tailgating, man. I'm out in the yard. You see the trees behind me. I got some motors out here in the back of my truck. We're going to test some motors. So,
All right.
I told when I got all this stuff loaded in here, I thought about what's his name on Saturday Night Live, the old Saturday Night Live. It was it wasn't Dan Aykroyd. It was Steve Martin. He's the one that said, "I'm a wild and crazy guy."
Yeah.
He's, "I'm a wild and crazy guy." When you look in the back, you look in the back of my truck. I got all this stuff. I got these motors in here, and control board, computer, all this stuff. And I'm tailgating, and I got some mules behind me out here. I got the mule stables and all that. So people riding by are probably wondering, what's that King feller doing out there? Is he all right? Let's see. Is Justin with you, Thomas?
He's in there eating supper right now. He'll be here in a little bit.
Okay. Now,
Darren's in there with him too. You hear me?
who Darren's in there?
Yeah, Darren's in there eating with him.
Okay.
They'll both be in here in a little bit.
Okay. Good. So after frame size, again, that's your international selections, your NEMA US, and then voltage. Most motors are dual voltage, and they can run low voltage. If it's three phase, then most three phase motors are going to have a choice of low voltage being in the range of 208 to 230 / high voltage 460. And so if you're running in the low range there, then you're going to have, this is your connection. That's how you wire the motor. So you've got 9 wires on the average motor. Some motors have 12, but a lot of them have 9, and some have 6. It all depends on, if it's a dual voltage motor, the average one, it'll have 9 wires on the average motor. I know at Schindler you've got some other things. You've got some 6 wire, but when it's that way, they're dedicated to 1 voltage. They're not like dual voltage. So they're bound that they'll only run at 1 voltage, and there's not as much to wiring them. But with that wiring diagram there, can y'all see that?
Yes, sir.
So here you have your power line coming from your motor starter would feed into here, and it would connect with 1 and 7. So T1 off of the starter would join with 1 and 7. It would give you 3 wires together in a wiring up. Your line 2 off of the starter would go to 2 and 8. Line 3 goes to 3 and 9, and then 4, 5, and 6, they'll just go in the wiring up. Now, not many of you wired 480 in our shop, but we're going to go over that. And basically, that same motor could go 460, and it would actually run on 482. So the same motor, when you configure. Yeah, I hear you.
It's me and Darren Olivia.
Okay. Y'all been hard at it.
Oh, yeah. Wide open, but wide open.
How's your leg doing?
It hurt my heel.
One day at a time.
I took the Youngster stuff.
Hang in there. It'll get better.
Yeah.
It'll grow back together. You're young.
It might.
All right. So if that same motor, if you're gonna wire it up high voltage, then here it is. Then coming from your starter, your line 1 is going to simply go to 1. Line 2 from the starter, it's just going to go to 2 in the motor. Line 3 from the starter, it goes to 3 in the motor. And then you have, you put a wire nut on 4 and 7 within the motor, another wire nut on 5 and 8, another wire nut on 6 and 9. Okay. So that, again, that's something that quite a few people didn't get a chance to do. And with the motor that I have here, we're going to go over that whenever I get the camera set up on that. We'll go further in the book before we do that. So actually, I've already got this one set up on high voltage because when we do a test on the motor, it's best to do it at the highest voltage. So I can show you real quick how. Let me get my camera flipped around.
Jameson.
Yes, sir.
I said Jameson. He look asleep over there.
Boy,
Hey man, you turning 32 tomorrow.
Yep.
I put a big thumbs up on the screen.
Lean this down. Get you a good view. So right there. So I'm gonna cut off screen. Well, I better not cut off screen share. How well can you read that?
Not at all.
Not very well at all.
No.
How about now?
Still can't read. Hold on. Wait a minute. Hell, it might must be us. That didn't work.
You may have to maximize that screen view.
Yeah. We see it now. You good?
Okay, I see where it's blurry.
Yeah.
Now I've got an autofocus that's coming that it'll be any day. If I back it up, now that fixed it, didn't it?
Yeah.
So what it is, this camera does not autofocus. If I get too close, it's blurry. So I basically got to set the spacing. So everybody in the class wired one low, okay? But high, everybody didn't. So let's go over that. So basically right over here, I've already got it set up that way. So coming from your starter like that, you got your 1, 2, and 3 coming off the starter there. And so let's see. That blue wire is number 1. That's the number one. That's going to go to the first leg leaving the starter.
Right.
And your two right there. And that's really small. You probably can't see that.
You can see it a little bit.
Or maybe you can. That two, okay. So that two there, that two goes to the second leg on the starter. That three right there, that three goes to the third leg on the starter. So you have 1, 2, and 3 single legs going to the starter, and then the rest of it is going to be pairs. So you have a pair that's a 4 and 7 with a wire nut, a 5 and 8 pair, and a 6 and 9 pair. So let's come over like this, and let's take a look at the pairs. So you have I think I can get it even closer.
Yes.
That's still blurry, I know. That's blurry, I know. Let's back it up.
Mm-hmm.
That's probably when I get the auto focusing camera, then it's going to be a lot better. But that's going to be for the summer class starting up on the 18th.
Yeah.
But the yellow, maybe if I go at an angle like this.
Yeah. Apparently, I'm watching this. Oh, that's your problem.
Well, you can kind of see that. But right here, you have the yellow, and the pink. The yellow is 4, and then the pink is actually a 7. So that's 4 and 7. You notice there's only 2 wires in a wire nut, and then you have 5 and 8. There goes your 5 and 8 right there. I know it's hard to see it, but black is 5, and then 8 is red. That's 5 and 8. And then I just lost a wire nut for 6 and 9. So there goes a 9 with a dot. There's a dot there at the bottom of the 9. So on your wire labels, they'll either have a line under the number to know whether it's a 6 or a 9, or there'll be a period, a decimal on the bottom right of the wire number, so that you can recognize what the digit is. Now, I know my camera is not detailed enough to be sharp on that. But I have ordered a better camera. We're going to put 6 and 9 together there. That camera went with about $114 from my Granger. So that's the 6 and the 9 there, which is the gray and the purple, 6 and 9.
Hey, Durwood.
Uh-huh.
That ain't no cows in the background, is it?
It's mules and donkeys.
Oh, all right.
Sure is.
No.
Yep. The guy raises mules and donkeys and sells them. Byron Herring. So one thing to take note of here is that if you're dealing with a 9-wire motor, here, it's got wires 1 through 9, is in your on high voltage. Every wire nut has 2 wires. Everything's in pairs. Everything's in 2s. Okay. Even your incoming wires, when you tie these to the starter, you've got your wires coming into this from the starter, and that's going to give you two wires per wire nut. You know, you have a 1 and a 2 and a 3 coming in, so everything in that cat head is going to be in pairs. If it's wired high voltage, does that make sense?
Yeah.
But if you wire low voltage, then everything is going to be in 3s. All the wire nuts over here, like what you wired at the school, there's going to be 3 in each one, because the incoming wire from the starter is going to join with a 1 and a 7 in the motor, and that's going to put 3 wires together in that wire nut. And your line 2 from the starter will join with 2 and 8. That gives you 3 wires. And then your third leg from the starter, it ties with a 3 and 9, it gives you 3 wires. So everything's in 3s. And then you get 4, 5, and 6 together. That's also 3. So it's everything's in 3s, everything's in 2s here. So when you go to replace a motor, that's a giveaway. If it's a 9-wire motor, it's all in 2s here and it's all in 3s here. So that's just one thing that's worth looking at. Okay, any questions? Okay, then we flip back to the chapter. Let's see, do screen share. Okay, so that was your voltage, dual voltage. Get right and flip. And then FLA is full load amps. So the full load amps is going to be if the motor actually has a load on it and it's actually driving a gearbox or a pump, then you could expect it to draw in this range of amps, 3.8 amps to 3.6 amps, if you are wired on low voltage. So when you're wired at 208, the motor would draw 3.8 amps. If you're wired at 230, when you increase voltage to the motor, the amp requirement goes down, so it goes down to 3.6. The motor doesn't want as many amps whenever you raise the voltage, because it basically, when you multiply the voltage times the amps, it's going to give you power consumption in wattage, and that power consumption is roughly the same whether you're at a low voltage or a high voltage. If you multiply the 230 times the 3.6, it's going to give you so many watts or kilowatts. And then and at 460, the amps actually goes in half. That's exactly half of the 3.6. So if you double the voltage, then the amps goes in half. But when you multiply the 460 times the 1.8, what does that come to? Just curious. If you multiply that out on your phone, calculator, how much?
828.
828.
828. Now, so is it the same number if you multiply 230 times 3.6?
Yeah.
Right. So what we're getting at here is this. Some people think that just because when you double the voltage and the amps goes in half, they think they're going to get by running the motor cheaper. But you're not. You're still paying the power company the same thing for wattage. You're paying the power company for kilowatts per hour that you're using. And so the volts times the amps is going to equal watts. And the wattage consumption is the same whether you're at 230 or 460. The only advantage of going 460 would be you can use a smaller wire size. So your wire size does go down. You don't have to have as large a wire whenever you go low. Whenever you go high voltage, your wire size can go down. So, okay, now moving right along is the enclosure type, and the ODP means open drip proof. I believe that's what that means. If you look on page this is important if you're going to be around wet areas. Yeah. ODP means open drip proof. And if it said, I'm reading on page 363. So this information right in here for enclosure, it could say TEFC. That will be totally enclosed, fan cooled. And then if it said EXP, it would be explosion proof. So some motors are explosion proof. They can actually be used in flammable areas. or maybe around in feed mills or where you got explosive dust particles around in a feed mill, for instance. Okay. The continuous duty. Well, the duty cycle, is it a continuous duty motor, or is it one that's not rated to run all the time, which would be an intermittent duty. Most motors are going to be continuous duty, and then maximum temperature. What that's referring to is it's actually referring to temperature rise. So that 40 degrees C would be, that's how much rise in temperature that motor could exhibit above ambient temperature. So whatever room you're in, you could expect that motor to actually be, it could run at 40 degrees C higher than actual ambient temperature. So it's giving you a rough ballpark on how hot the motor could actually run above ambient. Service factor, what it does is it tells you, you multiply that number times horsepower. So here, this motor is rated at 1 horsepower here. But if you multiply the service factor times the horsepower, what it means is the motor could actually deliver 1.15 horsepower if it got in a strain. So whatever the service factor is, you multiply it times the horsepower. It gives you the true horsepower the motor could deliver without being damaged. Okay, so you multiply that, and then the code letter is okay, your code letter is referring to locked rotor current. So when the motor starts up from a dead still, they call that locked rotor current. So K is a code that can help you calculate what the starting amps would be for the motor if you wanted to know that. So that you can look on page 364 and 365, and it tells you, it gets into calculating. Actually, the code letter, if you look right here, if it goes forward right there, this is showing you if the code letter is K, then you would multiply that kVA, which is kilovolt amperes, which is like wattage. kVA is like saying wattage because it's volts times amps. They put a K in there, it's thousands of thousands of volt amperes or thousands of watts. Volt amperes is like saying watts. So if it's a K type code, then you would multiply this. Actually, you multiply the mid-range number of 8.5. You would multiply that times the kVA rating for the motor. You multiply that times the kVA rating in the motor, and you divide it by the voltage, and it's going to tell you the starting amps of the motor. There's an example. I'll show you with the webcam. Let's see, right there where I'm pointing there. If you look on page 364, it's showing you right there that you can, if you have, let me get my cut screen share off right quick so I can tell if I'm focused right or not. Okay, so now you can see that their example is this: is they have a 15 horse motor, 3-phase motor at 480 volt, and it has a locked rotor code of J, and the J comes from down here. So the J has a mid-range value of 7.5 kVA, of 7.5 per kVA. So for each kVA of the motor rating, it's going to be 7.5 times that. So if you go back up to here, you calculate the starting amps of a motor by doing this. The actual startup amps or the inrush would be this. It would be the horsepower of the motor times the kVA factor. Okay, that factor that you got from down here, which is a 7.5, because it's a J code, 7.5. So you take the horsepower of the motor, in this case it's 15 horse times 7.5. You multiply that, you got to divide it by the voltage, which is 480, times the square root of 3. The square root of 3 is a factor, 1.732. You have to figure that in with three-phase to adjust the voltage there in three-phase system. And all of that comes down to 831 amps. That's the startup amp. That's the startup amps for a 15 horsepower motor, three-phase at 480. So that's a lot of amps on startup. That's called the locked rotor amps there from a dead still. I'm sorry, 135 amps. My bad. The answer is 135. I'm trying to look at the camera plus this. So the top two numbers, when you multiply 15 times 7.5, it ends up to be 1125 kVA. Ends up to being 112,500 volt amperes divided by 831 gives you 135 amps. So that's the startup amps. That's your inrush for a 15 horse motor, three-phase at 480. So that's kind of an engineering level type calculations there that not a lot of people would be concerned with that, but that's how, you know, that's how the code letter comes in. If you needed to know that, in most cases you don't really have to be dealing with all that, because someone else has already told you. You're just replacing a motor that somebody's already put in. So unless you're an engineer, you don't particularly have to know all that. Let's go back to screen share. And go. Next would be NEMA design. And your design code, it has to do with operating characteristics of the motor. And that's on 364 and 365. And that information is basically telling you stuff like this. If I go back to, I'm gonna move the camera around some so I can just show you what I'm looking at in the book. So your design code has to do with operating characteristics. It says motors with a code letter A exhibit normal starting torque and high to medium starting current. If you have a NEMA design code of a B, they're most common, they exhibit high starting torque and low starting current. If it's a C, they have high starting torque, low starting current. If it's a design D, high starting torque and low starting current. So that, again, that's information that's actually on the nameplate. That's your design, and whoever's picking the motor, you know, would be the one dealing with that. And then your insulation class, that's important if you're dealing with really hot areas like around ovens. So insulation class is, I go back to screen share. Go back to center. So that's efficiency. EFF, that has a 0.77 efficiency rating there. And then the insulation, INS, would be insulation. That's going to be on your temperature rating of the motor, how hot of an environment can it handle. So your information for that would be right here. And let me see if I can get this down. So if you can see, can you see on my screen all of that information there? If it has an insulation class of an A, if it's got a class A, then those are the temperature ratings that motor can handle. So this is a real biggie right here if you're around ovens. And if it has a B rating, it can handle up to 266 Fahrenheit. A F can handle 311 Fahrenheit. So you're talking oven duty motors there. And a H could handle as high as 356 Fahrenheit. So this is information that's very important if you're dealing with ovens. And I know you are at Smithfield. And let's see, I'd hit the wrong button here. So let's see. Next would be now the connections. We discussed the connections. That's for low voltage connection, high voltage connection, and then determining the motor current itself. There's 3 different types of motors, and there's different tables. You have the tables are in the code book, National Electric Code book, and they're in your book here. You got DC motors, which are actually kind of phasing out. Not many people use DC motors or direct current motors. You got DC motors, single phase AC, 2-phase AC, and 3-phase AC. So this chart here in the code book and also in your textbook, do y'all see that?
Yeah.
So that chart, 430.247, it's in chapter or article 47 in the code book. So chapter 430 is on motors. It's nothing but motors for that whole chapter or article. So if you ever get around a code book, if you get access to one, you flip to chapter 430, which is also called article 430. When you get to that whole section is on nothing but motor data. Let's see, where's my mouse at? So if you had a DC motor, for instance, if it was a 5-horse motor and it was running at 120 volts, it would draw 40 amps. So this is the amp ratings in here. A 10-horse would draw this, but at 240, it would draw half that. Okay. The next chart is for single phase AC motors, alternating current motors. These are your horsepowers and your voltage columns. So at whatever voltage that you're running at, you follow it down, and wherever they intersect that is going to tell you the amp draw for the motor for a given horsepower and a given voltage. And this is one that I've never had to use. It's on 2-phase AC motors. Actually, they say 2-phase 4-wire. I was thinking 3-wire, but it's 4-wire. 2-phase 3-wire system. But anyway, I've never seen one in a plant. I don't know if y'all have any 2-phase motors or not, but the diagram for one of them, just so you can see, would be that. Is you have a hot wire here and a hot wire there. You got 2 legs, and then those 2 ends of the windings in the motor are actually wired together to a common. So that would be a neutral leg right there. It is actually it's a 3-wire feeding it, but it's 4 wires in the motor. That's a 2-phase motor. It runs on 2 phases plus a neutral. And that's a picture of what the actual waves look like that are the 2 different phases, the A and the B phase. And they're out of phase by like 120 degrees. They're 90 degrees out of phase. When this one's at 90 degrees, that one starts at 0. So they're 90 degrees out of phase from each other. But the most popular chart for getting motor for this is for 3-phase motors here. So this is the one that you want to go to, and we're gonna do some examples of how do you know how many. Let's just say I'm gonna let one of you pick a motor size. Who wants to pick a horsepower size and a particular voltage, and let's see what the amps would be.
Five horsepower.
5 horsepower at what
Sure.
volt?
I don't know. 230.
230.
Yeah.
So what would it be?
15.2.
15.2 amps. Yeah. And then how about if somebody, say if you pick like a whole lot bigger one, somebody pick one down in here.
Like a 75,
75 horse at what voltage?
460.
At 460. Okay, so that would be your amp draw under full load.
Mm-hmm.
So can y'all see the 96 there?
Yeah.
Now that should line up. That should line up with your nameplate also. It should line up. But I can tell you that these numbers are they're middle of the road numbers that represent different brands. So you may find a slightly different number on a motor, but it's not going to be far off of that on a nameplate. It's going to be very close to that.
Sure.
And go ahead.
Yes, sir.
Okay. So here, these motors here, this chart is going to be for induction type motors, squirrel cage, and wound rotor. And then if you got a synchronous type motor, that's a more sophisticated type motor, more precise on speed, then it's a whole different chart over here. So it depends on the windings in there, what kind of motor, and that stuff will actually be, it would be printed on your nameplate. They're just showing a 2-phase motor, what the amps would look like. Each leg would have 10 amps, but the neutral would have 14.1 by having 2 different phases there. They're just showing you what that would. That's odd. I've never seen one actually in a plant anywhere. Okay, now, how do you pick the right size wire for a motor? This is very important because some people don't know how to do this. They don't know how to do it by code. And some people will they'll undersize the wire, and then they can have it actually to melt at some point in the conduit. So you pick the wire size or conductor size based on the National Electric Code tables that we just looked at. Instead of looking at the nameplate current, you actually get the value out of the code book for picking the wire size. And the reason for that is this. You may be running a ball door motor today, but you may end up with a lease in a year from now. So they get a middle of the road number from different brands, and what's in the code book would represent an average of motors, if that makes sense. So your nameplate could vary, but a leasing or a ball door may vary slightly, but the code book will cover you for either one of them. So you're going to go off of the chart that we just looked at to get the amps for the motor when you pick the wire size. And also, you also have to consider the temperature rating of the terminals that you tie to. So what we mean by that is this. You see that starter there?
Yeah.
The terminals that you tie to down here, your lugs, there'll be a temperature rating on those. And it's actually stated on the side of here. This one is rated at 75 degrees Celsius. The terminals have a maximum rating of 75 degrees Celsius as far as the terminals. So you have to keep that in mind. You got to keep that in mind when you pick the wire size. And we're going to see really shortly how where that matters. Now, this is where you get the amp rating for the motor, like we just saw. This is how you calculate the amps so that you can pick the right size wire. So basically it's this, guys. Just remember 125%. So whatever the amp rating is of the motor, if it's 10 amps, you want to multiply that 10 amps times 125%, which would be 1.25. So what's 10 amps times 1.25?
12 and a half.
12 and a half. So that's the actual amp rating that you actually got to size the wire by. So when you go pick a wire size, it's got to be based on 12.5 amps, not on 10 amps. Okay? So that's the first thing. if you read right here out of the code book, it says that conductors or wires that supply a single motor, if it's continuous duty, shall have an ampacity, which is amp rating, not less than 125% of full load current rating, determined by these articles in the code book. And all of that actually comes from right there. That chart with the amp ratings that we just looked at, it's what you go by, and you multiply that chart number by 1.25, and then you go pick a wire size. So let's do that. Let's do a couple of motors. Let's do two motors, and let's figure out the right wire size. Now, so I'll take a volunteer. Whoever wants to volunteer.
Thank you.
Now, okay. So let's pick a motor size and a voltage.
Go ahead, Victor.
350. Pick a big one.
A what?
350. Pick a big one.
A 350. So you got a 350 horsepower motor right there. And let's come across to the voltage. So what voltage do you want to run at? You want to stick it at 460?
Yeah.
Yeah.
So
Sounds pretty common.
now it is. That's 414 amps. Now we got to take that times 1.25. So what is that? Everybody get out your calculator and do this, because this is the important stuff here. Doing this can keep you from actually underrating wire and having an embarrassment later on with wire actually overheating and melting in conduit, and it could be an embarrassment later on.
518 or somewhere in there. 520, if I had to guess.
517.
Now, so you said 350.
Yeah, there you go.
414 times 1.25, and I got what'd you get?
517.5.
517 amps, 0.5. So you got to go up. So it will be 518. So listen, that 518 amps, you take that, and now we're going to go pick a wire size. So let's go forward to the wire chart, and look, this is the wire chart right here, guys. So this is in your book on
372.
372. What I would do, take your phone and take some pictures in your book of these key tables, and you'll always have them. It won't take you won't really have to look in the code book for everything. So we're talking 518 amps. Now, the first thing we got to do, guys, is this. Now look careful. We got to figure out what column are we going to be in for temperature rating of the wire. Now, let's give you a real scenario here. So you see that starter I have here?
Yes.
Say, for instance, that you have a starter and the temperature rating down in here says a maximum of 75 degrees Celsius on those terminals. Now, let's say that you've actually got some wire in the plant that you typically use just rated at 90 degrees Celsius. The wire can actually handle 90 degrees C. It's okay to use that wire. But if you got that wire, you can't get the amp rating out of that column because the terminals are rated one column back. You got to go with the lowest rating on each end of that wire on the terminal. So you have the starter here, and then you got your terminal strip you're tying in a motor that you're tying to, right? So if it's 75 degrees Celsius here because of the rating stamped on here, let's just assume that, because a lot of times that's what it is. So here you got to use this column right here, the 75 degree column, to rate the wire, even though the wire insulation may be something over here in the 90 column. You got to fall back in that 75 column because of the weaker link being the terminals on the starter. So 518 amps, so what size wire is it? You got a 490 amp, 520 amp. We're talking 500 and, well, okay, so which one?
Glad to go with the 520 to 900.
Right. So 520 amp rating here, and listen, what size wire is it?
900.
It's a 900 KC mil. The KC mil is K is 1,000, and C mil is circular mil. So it's a 900. Hold on, a 900 KC mil conductor. And again, that's thousands of circular mils. So it's a very large conductor, very large. And it's very likely that it wouldn't even be a single wire, but it would be multiple wires per phase, more than likely. They would probably have several conductors per phase on that motor. And because it would, I've never seen a motor would wire that big, and I don't even think they would even do it. They would actually do parallel conductors that would be the equivalent of 900 KC mil. You know, they may go in there and do seriously. They may get three of these 300s right here, okay, to make a 900, and they may do three 300s per phase, and actually have them paralleled on some terminal blocks, large terminal blocks that are actually jumpered together. And I mean, I've seen pictures of things like that where you had multiple cables or wires per phase in a system. So that's more than likely what you would see there. Is everybody okay with how we figured that?
Yeah.
Now, the next thing is, the wire size. That's the minimum wire size. How about the overload setting? Now, you got an overload right here. How do you know what to set the overload to? Because it's got actually a screwdriver adjustment on it that you can turn with a screwdriver to set the trip rating on the starter. So how do we know what to set that on? Well, believe it or not, it's the same number. It's that 125% that we had. So the 518 amps that you just calculated, that's what the actual overload would be set to. It's the same number that it's 125% of your full load rating. So that actually comes. Let me go forward. Here, your overload size. The overload size is actually based on nameplate current rating of the motor used instead of the table values. Now, the reason why that is because, look, whatever specific motor that you're running at the time, whatever brand it is that's out there, you can physically go up to this overload here and take that screwdriver, and you can actually fine tune that right on the fly for whatever motor that you have. So you actually dial that in, you take the nameplate amps. If the nameplate amps said what the chart did, and it's going to be close to it, you get the actual full load amps off of the nameplate and multiply it by 1.25, and it's going to give you the setting, for that overload. And that's what you dial that into so that the starter would trip out safely. So the numbers that I just said, they come from right here. So if you look right here, this comes right out of the code book. It says that if it's more than 1 horsepower, you have to have a separate overload device. And for most motors, it's going to be 125% of your full load amps. If it's motors that don't meet this criteria, then it's going to be 115% that you set the overload to whenever you dial it in. But you use information of service factor. If your service factor meets that criteria that's on the nameplate, then you set your overload at 125% of your amp rating on the plate. Or if your temperature rise on the nameplate is 40 degrees C or less, you also figure your amp rating at 125% of your nameplate. So that tells you how to set the overload properly. Now, one thing that the book didn't get into, and I've included it in here, is this. You see over here on the right side of the screen where it says 140%? You see right over here?
Yeah.
Yeah.
That says 140. This says 125. So it says in the code book that where your settings, if you set that starter and you have a flywheel press or something like that, that's Jamie, where you're at, those big old punch presses,
Yeah.
it takes them maybe 20 or 30 seconds to get up to top speed. Let's say, for instance, that you got a punch press and that motor is belt driven, and it takes it 30 seconds to get up to top speed. And guess what? It's probably going to trip out if you set it for that before it ever hits top speed. So you're allowed to come over here to 140%. It says here that where your sensing element or overload size is not sufficient to start that load, a higher size is actually allowed as long as you don't go above 140%. All right, so what would it be for the motor we just looked at? The motor we just looked at was, what was the original number on the amps? The original nameplate number that we looked at.
I don't remember.
Right, let's go back to here. It was a 350.
414.
Right. You go back to that number there, that 414, and you multiply that by 140%. So 414, you take that original number off of the chart, and you multiply it by 1.4. That's 140%. So 414 amps times 1.4 instead of 1.25.
So it'd be 580.
580 roughly.
580 amps. So listen, that would be your worst case setting on the overload there. You can set the overload at 140%. If 125% is not enough, if this setting over here is not enough, you can go at 140% for loads that are heavy loads on startup, where it takes them a long time to ever start up. You can do that. Okay. So that gives you your wire size and your overload size.
Those two charts you just had, are they in our book, or are they just in the National Electrical Code book?
No, it's in your book. So look, that one right there, where we got the numbers off of.
No, the one where you done the 140 while ago.
It's in the code book. They didn't include it in this chapter, but it's in the code book.
Okay. Hold on, let me write that down because I want to get a copy of that.
That right there is actually, it's in the same article. If you look right over here, article 430.32. If you read further past this in the code book, it actually gives it to you right after this. It's like on the very next page that it tells you can go 140.
Okay, I got it.
Wouldn't you have to go? You had to have your wire size bigger too, wouldn't you?
Now that's a very good question. My personal opinion would be yes. My opinion would be you got to use some common sense with this stuff. When you go up in them higher numbers like that, then my opinion would be you need to go back to your wire size and say, well, if you're going to sit there and run it at 580 amps, if that's your overload trip setting, then let's go back up to the wire chart. All right, we're in this column here, okay, because of the terminal ratings. And so for 580 amps, what wire size does it need to be?
1250.
1250 kc mil. So that changes things, doesn't it?
Mm-hmm.
Now, me and you, we're thinking exactly the same, because if you don't think that way, you're setting yourself up for some serious trouble that could happen easily, because motors go bad, the bearings go bad, the motors get bound up, and when that happens, if your wire cannot handle the trip rating on that starter, you're in trouble. That wire's going to melt. You're going to have a meltdown at some point. It's likely. It could happen. So I've heard stories of Butterball of them having to pull wire out of conduit that was melted together, and where things weren't rated right, and so that's a very good point there. So would you want to pick another motor size, or do you feel okay with what we just looked at?
I'm good.
Okay. Doing a big motor is actually better because, you know, if you can do a larger one, of course, you can also calculate for a smaller one. It's the same method. If you wanted to do another one, you let me know. Otherwise, I'll click on so we can actually get our hands on testing the motors. Right there is where they mention in the code book about your terminal ratings there. It tells you that your temperature rating of your wire, it's got to be selected not to exceed the lowest temperature rating of any of your terminals or connections or devices. So it's basically whatever the weakest link in the circuit is on each end of the wire, the lowest rating of each end of the wire. That's what you got to go with when you choose what column you're going to choose the amp rating from. It has to be based on the weakest part of the circuit, which a lot of times it would be the terminals. So some terminals are rated at 90. I've seen them that are rated at 90 Celsius, but I've seen more of them 75. So we've already looked at lock rotor. We've already looked at how to calculate that. Those are charts that already calculate for you what it is, if you had to know. What this chart tells you is it tells you about your fuses or your breakers that actually are upstream from above. Okay, you got your starter right here, right? So here's your starter. Now, what's feeding the starter would be some fuses or a breaker that would be feeding into the starter. So that's where this chart comes in. Is what's your protection above the starter? All you got to deal with from motors is going to be this here, fellas. You're going to be in that column there with time delay fuses for motors. Motors are going to use time delay dual element fuses. That's your percent right there. So if you got a 3-phase motor, they call it polyphase. You can rate your fuse above the starter at this, 175% of your motor current. So you can take your motor current times 1.75, and that would be the maximum fuse size you could use. You don't have to go that big on the fuse, but that's the maximum size that you could use on fuse sizes. That's actually above the starter. Now, the last column, if it's actually a breaker, a circuit breaker above the starter, it's going to be an inverse time breaker, not an instant trip. You don't use instant trip on motors because they're going to trip all the time. So an inverse time breaker, what it does, the name inverse time means this, is the higher you go above the breaker rating, the shorter the trip time becomes. So if the breaker is rated at 100 amps and you go at 110 amps, it's going to take that breaker quite a while to trip. But if you go with a 100 amp breaker and you draw in 200 amps, then the time actually shortens as the amps increases, so they call it inverse time. So if the time gets short, the higher the amps goes, the time gets shorter. The actual trip time becomes quicker the higher you go in amps. If it's an inverse time breaker, it starts out not being so quick for motor ratings. It gives time for inrush if you're a little bit over, but if you're a whole lot over, like for short circuit conditions, then the trip time is quick. So if you look at here, where's my pointer at? The percentage is 250% on a breaker. So if you got a breaker that's ahead of a starter, on top of a starter, you can take the amp rating of the motor and multiply it by 2.5. That's 250%. And that's your highest rating for a breaker that goes ahead of the starter. You don't have to go that high. I personally would not, go that high, but you're allowed to go that high if it's actually a breaker that's ahead of the starter instead of a fuse. So that column there, the last one and the second one, you're either going to be in that fuse column or that breaker column for a motor. And whatever kind of motor it is, you follow that and go across. So polyphase is going to be like 3-phase or many. Poly means many, more than one. Okay. Does that make sense?
Yep.
Okay, now let's try to get quickly to the actual hands-on of doing the motor testing. Now those are actual standard fuse ratings that you can buy off the shelf. They come in those increments there. And just remember that if you're picking a fuse, you can't go any higher than 175%. So whatever you calculate to, you're not going to, you can't go up to get to the next fuse size. You'd have to actually go back. If your number you calculated up here, if it actually falls, it's going to fall probably between some fuse sizes. And if it does, if it falls between these two, you got to back up to 175. You can't go up to 200 because you'll exceed, you would exceed you would exceed that 175%. You're not allowed to do that. Okay. Starter size. So how big of a starter can it be? It's going to be a NEMA size, a NEMA 0 and a 1 or 2, whatever. So right here, your NEMA size 0 would handle these voltage rating motors at these horsepowers. A NEMA 0 could handle these voltages at these horsepowers if it's single phase or 3-phase or polyphase. Say over here, a NEMA size 4, it could handle a 460 motor at 100 horse. A NEMA 4, it'd be a whole lot bigger than what I got in my hand. A NEMA 5 could handle a 460 motor at 200 horse. And so that, everybody okay on that?
Yeah.
So that for NEMA, that's how you would use it. For IEC international, you would still go by horsepower, voltage, amps, and then it would give you a letter like a IEC A or B or C. So the IEC sizes are actually in letters. If it's the European type ratings. Everybody okay with that?
Yep.
All right. And then overload sizes. Let's see if I can get a light on. I actually need to get a light on out here. Hold on one second. Well, you can actually see me still pretty good, can't you?
Yes, sir.
Right. I'll get a light to put on the motor here in just a minute. We're getting ready to show you how to test a good and bad motor. What that chart is there that chart is for actually separate overloads that are not adjustable, overloads that actually bolt into a starter that are fixed overloads. So actually I do need to get a light. Let me grab a drop light, guys, and I'll just 1 second. I'll be right back. Well, I may just bring the hold on. I'll bring my cover lid down. Well, that still ain't going to get it. I still got to have a. I got a drop light. I'm going to hang it up here.
Hey, Victor.
Yes.
Hey, so how's it out there at Smithfield with everything going on out there?
Not so good right now.
Yeah, I heard y'all had somebody in critical condition.
Well, they kind of hide all the information, but I know there's like 5 cases on
There's
the
7 now. That's
7.
what the paper just released.
Oh damn! I didn't even know that. I know it's just rough right now for maintenance and production.
Really?
I still have to be there.
Okay, I got me a drop line here, guys. It's what I use when I run my generator, when I have to get out and put gas in it. So I'm gonna hang this thing up here. Let's see if I can find my plug. I'll also be out here on this tailgate Thursday night because I have a VFD out here that'll run on. It's a single phase in, 3-phase out. I'll have it out here from school, and we're going to go over measurements, program the measurements using an oscilloscope and a multimeter. Just some in-depth stuff that I don't know if you've had a chance to learn. Okay, so now I got my light. Let's see. Hang that light. If I hang it right there. I think I can hang it on my garage door, man, and it'll be all right. Yep. Somebody said he's a redneck. Let's see. Okay. Yeah, I got my spotlight. I got a light hanging up here. It actually looked pretty decent right here. So so next thing, just cut that off. Now, so is it okay if I just kind of roll on with it instead of stopping, or would you rather me stop and take a break?
Let's roll on.
That's what I'm thinking, and then we once we cover how to actually physically do the testing, then we'll be done. I don't want to hold you guys long. I've been bad for that, and I don't want to do that. Okay, so that chart there, basically what it says is it tells you how to pick specific overload sizes when they're not adjustable. So let me just show you the difference between an adjustable overload and a preset one. Okay, so I brought the actual motor control bucket. I brought one here that come from Butterball. So let me move this here over. My screwdriver. Now let me get my webcam. Let's see. This here set.
Dang, Jameson, what you got going on over there?
Trying to keep it interesting.
He's got a background thing.
Yeah.
How you get that?
You got a choice in Zoom that you can put a background to it.
Yeah, down where you click the mute button, there's a little arrow on the right. You can click it up. It says choose virtual background. All you got to do is upload any video on your, any picture on your PC. And
Oh, okay.
so you can actually,
Look like you had so much money you sinking down in it.
yeah.
Now, if you look,
It's the what do you call it? Inverse timer. That's the inverse of that.
right.
Seeking down in bills, not seeking down in money.
Now those part numbers are like an X21 or X whatever. It's going to tell you how many amps that overload would actually be calibrated for. It's a fixed overload. Let's take a look at what a fixed overload looks like on a starter instead of an adjustable overload. So I'm going to switch over I'm going to cut screen share off so I can see what I'm doing with the camera. And I'm going to show you.
Otto way.
Now, you see that motor control right there? Y'all see that?
Yeah.
Now, look, I'm going to take this and loosen this up. This actually came from a butterball plant. It's an older starter that's actually got fixed overload. You slide this over like that and go down, and then you got the starter in there. You see that?
Yeah.
Now, below the starter, you got your overload. So I'm going to flip it up like this. Now, so now you're looking at the bottom. You see the overloads down there?
Yeah.
Everybody see those?
Yes, sir.
Now, you see those 2 screws? You see those 2 screws right there? So let's go in. How about now?
Yep.
2 screws. These are separate fixed overloads that are not adjustable. Now, an adjustable overload is going to be this. So you're liable to run into either kind. So this one here, that has a knob that you can adjust. You see that?
Mm-hmm.
This one here goes from 9 amps up to 45 amps. So it can handle a wide variety of motors. Once you do your calculation, we just went over at 125% or 140%, then you dial that in for a particular motor. You got to be careful what you do with this. You go too high with that, you'll end up smoking some wires or smoking a motor probably.
We won't.
Say it again.
We don't want that.
No. So the calculations we went over at 125 or worst case 140%, it's what you want to do with this, and size your wire accordingly. Boost your wire size accordingly, whatever you set it to, so that you're not going to have a fire hazard or personnel hazard, somebody, getting hurt. So this is adjustable overload right here. This adjustable. Now, here's one that's not. So this is one that you could easily run into. And again, the lid, the starter, is up top. That's the actual starter right there. So I'm put going in. This is actually a NEMA. What size NEMA is that? Can you read that?
Size 1.
It's a NEMA 1, and it can run 115 volt or 230 volt at 3 horsepower. 3 horsepower at 230 volt. Okay, so that's where your NEMA numbers are, and you see physically how big of a starter that is. It's pretty good size, So your starter is actually bolted into your overloads. We flip this back over, and now let's take the overloads out. I want you to see what they look like. So here I'm going to take one of them out.
Those are heaters, right?
They're heaters, yeah. They're just heaters. You take the screws out. So when one of these actually burns up, now when it trips, you just simply press that button right there, and it'll actually reset.
Yeah. Okay,
I'm going to show you. If you want to test this, you press in that red button right in there. You press that red tab, and it's going to make it trip. You'll hear it. Listen. Well, you might not have heard it, but it clicked. When I pressed that in, it actually tripped it.
I heard it, I think.
Now, when it tripped it, down here at the bottom down there, these two connections here, that's your normally closed contact right down there that you wire in with a coil. So when this overload trips, you lose a connection between this one. That would be like your 95 and 96 on what you've been doing. So that's your normally closed up under there, and it actually pops open, and you see that yellow indication in there?
Mm-hmm.
That yellow says you're tripped. Now, if I hit reset, the yellow goes away. You see that? It went back down in the hole. You see that?
Yeah.
So if it's tripped, the yellow comes up at you, and if you successfully reset it, it goes back down in the hole. Now, let's pull one of these out and let you see what it looks like. So what can happen is somebody can reset it so many times that it actually burns one of these heaters open, and it will never reset. So we're talking an operator, Jamie, that kept resetting it. He snuck in the panel and he didn't tell you, but he's already reset it 10 times, and you've actually got bad bearings in the motor. He keeps resetting it. And then after it won't reset, then he finally calls you. So if you look now, can you see what I'm doing here?
Yeah.
So look, you got to gouge it out with a screwdriver. And this is an overload heater, and it's a fixed one. And what does that look like? You see those coily lines there?
Like a heater element or something?
Yeah, it is a heater element. Yeah, that's what it is. So on the front of it, it's got power in and power out, but it's actually going through the heater element and then back out. So it actually is a heater element. Now, so this one is a FH32. You see that number on there?
Yeah.
So that part number correlates with a particular amp rating. That may or may not be the amp rating, but it's a FH32, it looks like. So it's not going to be 32 amps, though, I know that. But that part number, you got to go to a chart, like in the book. The chart we just looked at, that's on page 380. You go to page 380, and it gives you the let's see. Those are heater part numbers right there. They're X numbers, so I don't know what brand that is, but whatever brand it is, you'll have a chart. If it's Allen Bradley or Snyder or whoever it is, and there'll be a dedicated part number for so many amps. You see that?
Mm-hmm.
It says heater type number. So there where everything is in X something, this one is it's a FH. But see, this is Cutler Hammer. Cutler Hammer it had their own numbers. So and that's actually Westinghouse. It's Westinghouse. If you see down in there, it's actually a Westinghouse. So all these part numbers on the heaters and all, they're going to be Westinghouse numbers. So but anyway, so getting back to this. So if you look down in there, you see that hole in there?
Yeah.
That's where that heater element goes down in there. So it senses motor current. If it gets too hot, what it does is it actually bends. And when it bends in there, it flexes. It's going to trip a mechanism in there. And when it trips a mechanism, here's what's going to happen. These two wires down here, that normally closed contact's going to pop open. So that is your normally closed that's actually tied to your coil. This actually will disengage the coil if it pops open. So and the way you can test that, if you wanted to test it, well, let's go back in with this thing first. So you just drop it in the hole like that, and put your screws in. Butterball donated all kind of stuff, and it's a good thing because sometimes the equipment that you work on, Victor, do y'all have any stuff like this at your plant, or Patrick or McGill? Do y'all have any fixed heaters like this that are not adjustable?
Yeah, some of our older stuff is like that.
That's right. Your older stuff is that way, and it'll be a specific amp rating. And when they burn open, you got to go to your parts department and get that right number there. If you get some other number, you could either be tripping prematurely or not tripping early enough and end up again with a hazardous condition. So but that again, everybody okay with that?
Mm-hmm.
Okay. So, the fuses and all that are in here, they're going to be those dual element time delay. Anything in motor controls are going to be those ones that have a time delay to them. And so this would be actually in there to protect your transformer, which would be for your start stop circuit. That transformer would be in there for your switch. You got your switch here. So if you're going to go in hand, the starter's going to come on automatically. The control power up here for that and that light is going to come from that transformer down there. And your main power comes in through that circuit breaker there. Let's see. That's your main circuit breaker over there. And then there goes your starter. So circuit breaker disconnect with the handle and all that. So it's an older one, but again, they're still using them in some places. So so let's put this up. So next thing is let's look at how do we test a motor? How do you know if it's good or bad? So let's get this bucket here out of the way. I got a truck bed full of stuff. I bet some people going by saying, what is that King feller doing over there? What's that King feller doing? But ain't none of them slowed down though.
Might think you're building a bomb over
there. Lord have mercy. Okay. So next thing. Let's see. We go. Let's go back to where are we at? That was that's for fixed heaters versus adjustable. And let's see. Calculations. We've already been through enough calculations that you've got the gist of how to do those. So let's go over. You can actually study those, and if you got questions about any of it, you can let me know. So now let's flip over now to the webcam, and here the motorcycles going by.
Yep.
Yep. Got a good breeze out here. Okay. Let's go. Jameson, you didn't go to the beach. It looks like he's at the beach, man.
Yeah.
And Victor.
Some beach somewhere.
Victor, you got a lot of brain power. You got all them lightning bolts coming out of your head.
Yeah, man.
You must be a powerful dude, man. Okay, now, so let's focus here now on the motor. I've got that motor. It's a 9-wire motor. I've got it wired high voltage, and I've got the 3 leads right here out here to where they can be tested. The motor's already been configured for high voltage again. That we did that earlier. And I have a ground wire here. Now let's take a look at the construction. There's 2 ways a motor could be wired, and let's take a look at them. Now, I'm trying to remember. I think I emailed you guys what you're getting ready to see. Now, did you get an email from me that showed that?
I don't remember.
I don't remember neither.
Now, I emailed, I'm pretty sure I emailed everybody.
Oh, yeah. On the school email.
On the school email.
Mm-hmm.
You guys go back, and it's a good thing if you go back and save these things, and also save them to your phone. and maybe even print you a couple of copies to go in your toolbox at work. So look, motors, when you're dealing with a 9-wire motor, which a lot of them are, and if they're dual voltage, they're either going to be constructed internally in a Y configuration that looks like the letter Y, but they spell it W-Y-E. That's technically a Y configured motor internally. So inside of the motor here, do you still see my webcam or not?
Yeah.
Yeah.
Inside that motor now, it doesn't tell you on the plate that it's a Y, but there's a way to actually test it with a meter to know is it a Y. You can pretty much assume if it doesn't say Y, that it is a Y. And if it's a delta, it looks like this. So it looks like a triangle. Do y'all see that triangle? Let me go a little bit larger. Right, do you see the triangle shape inside that motor?
See nothing.
You don't?
No, I don't see what you're pointing to.
You don't see a delta wound motor?
No, we're still at the
You're still at the Y.
Webcam.
You're still at the webcam. Let me go out and do a screen share. I'm sorry. Let me minimize here. I've got to turn screen share back on.
Generally, the triangle is delta, though, right?
Yeah, triangle's delta. Yeah, but I need to do a screen share. I'm sorry. I thought I had them on the screen here. Let me go back to pull up. You got Y. Now, so do you see that Y there now? That Y?
Yeah.
mm-hmm.
So a motor's either going to be Y wound internally or delta wound. And you're talking the internal construction inside the motor that you can't see it from the outside. So we're talking inside that motor, you have one winding here with 2 wires, another winding with 2 wires, another winding with 2 wires, and then you got 3 sets of windings that are inside the motor that are a permanent Y. So here's what really makes it a Y, guys. If you see that right there,
Yeah.
this actually makes it a Y because you got that winding, and these 3 are actually permanently wired together with a dot in the middle. And that's what actually makes it a Y wound motor because you can't change that.
And it always be 7, 8, and 9.
It's always 7, 8, and 9. If it's a dual voltage 9-wire motor, it's always going to be 7, 8, and 9. So,
Okay.
so how do you know? How can you tell if it's a Y or not with a meter? All you got to do is this: you put a meter, an ohm meter. You make sure that the motor's unwired, like I got right out here. It's unwired. You put an ohm meter on 7 and 8 and see if it rings together. If it rings with the ohm meter, if you get a low resistance reading, and then ring it from 7 to 9 and see if it rings, and then ring it from 8 to 9, and you get a connection with all 3 of those wires with an ohm meter, and that's how you prove it's a Y wound motor because those three wires will always be connected together, and you'll get a reading with an ohm meter inside. Okay. If you wonder, is it a Y or a delta? That's how to tell. Now, honestly, if it's a delta, it's actually going to tell you on the motor. So if you go delta, you see the triangle there?
Yeah.
So a delta wound motor is everyone I've ever seen would always tell you right on the nameplate it says delta wound. Everyone I've ever seen always said delta. So delta is the one that you don't see all that much of in some plants, but at Schindler, it's what you see predominantly because at Schindler, let's just say this, delta wound motors have higher startup amps. So this type of a motor that's constructed like this has a higher torque on startup than a Y does. So this has a really strong startup versus a Y wound motor has more of a soft start to it. This doesn't draw as many amps. It doesn't have as much torque on startup as a delta does. Okay, so that's the primary difference. Now, so let's take a look at the Y and how do we test it? All right, you know how to wire it. Now, this is what's inside. Now look closely here. Now take a look here. If you wire this motor up high voltage, guys, look at here. You're hooking 4 and 7 together with a wire nut. Look at that. See that right there?
Yep.
You're tying 4 and 7 together, and then 5 and 8 down here. You got 5 and 8 together. See that? That's a wire nut there. And then 6 and 9. So 6 and 9. So you got a wire nut here, here, and here, and that puts all the windings in series. It puts them in series. So if you're on high voltage on Y, it's actually a series connection on the inside of the motor of everything. If you go low voltage like we did at the school on most of what we did, here's what you got. You're putting your first leg off of the starter on 1 and 7. So your first leg goes to 1 and 7. Your second leg goes to 2 and 8. Second leg goes to 2 and to 8. Your third leg goes to 3 and 9. So the third leg goes to 3 and 9. And then what happens, you got 4, 5, and 6 to go together. You see that? The 4, 5, and 6 go together. Now look at here. When you tie 4 and 5 and 6 together, what you've done is you formed another Y here. You got a Y in here, but you've got another Y constructed of this winding, and that one. And they form another center connection for a Y with 4, 5, and 6. You see that?
Right.
Everybody see that?
Yes.
Oh, you have a double Y. If it's parallel, if it's low voltage Y, it's called a double Y. You have a Y here, and you got a Y out here. There's 2 Ys, 2 Y wounds, 2 Y windings, and they're in parallel on low voltage. That makes sense?
Yeah.
Okay, so just keep that in mind. Now, when you test a motor, here's what you want to do. You want to wire the motor on the high voltage side so you get the best test out of it at the highest voltage on the test meter, because the test meter is actually going to produce high voltage and inject voltage into the motor and test it under voltage. Okay, so let's take a look at how do you do that. Now, first of all, if you look at the lab test over here, it's telling you put the voltage range that the meg tester or insulation tester, the meter is actually called an insulation tester. You see that right there where it says insulation multimeter?
Yes.
Yeah.
It's an insulation. It actually does multimeter functions like regular, plus it has an insulation test over here that it actually generates voltage in here, and it actually shoots voltage into the motor and finds any leakage that may be in there. So you have this is a more modern version, and the older one is a crank type. I'll get it out. So the older one is like this, and it has a crank on the side. You see that crank?
Yeah.
The older one, you actually have to wind it up like that, and it's actually going to generate voltage. It's going to shoot voltage into the motor, and it's going to detect, do you have bad windings in there, or are they shorted out? So we're going to use, if you're interested in learning how to do this one, I'll show you. If not, we'll stick with this. I'm going to let you tell me, okay? This is what most people are using nowadays, but if you want to take a look at the old style, you just say the word and I'll show you, okay? We'll let that be your call, okay? So your guidelines on your testing is going to be this. If you take a look at the sheet, you select the voltage on your insulation tester that it's going to produce. It's going to be near the rating of the motor. So I'm going to show you basically here. If you look on the meter, if I flip it to insulation test, I go over to here, and if you look up here, it says what, 500? Do you see that?
Yeah.
Now, if I hit range, it's going to change. What does it say now?
1,000.
If I hit it again, what does it say? 50. How about now? 100?
200.
250, and then 500.
Yeah.
So we're going to check it at 500 because it's a 460. It's a 460 rated motor, and the nearest voltage you can check it at 500. Okay. Now let me just show you something that's very surprising here.
You still got the screen share on.
Now, yeah, okay. Now watch closely here. We're going to check each motor lead. You got three motor leads right here. You're going to go from each lead to ground when you do this under voltage. You go T1 to ground, T2 to ground, and T3 to ground. So your reference point is going to be this. A bad motor will read less than 1 megohm, or one mega is going to be 1 million. So if you're less than 1 million ohms on insulation resistance, it's going to be considered to be a bad motor. If you're over 1 meg, then that's their borderline. That they say if you're over a meg, you can let the motor run, even though it is developing leakage. They say in general, that's a general figure right there. It's kind of sort of pretty much accepted. Okay, so let's go. Turn the screen share off, and this meter it comes out of a kit with a lot of leads in there. Now, this meter can also read amps. Okay, so it has the jacks here. If I wanted to use this meter checking amps, then basically what I do, I take that amp clamp and go down here to common here, and milliamps. And for every amp that it reads, it converts it into 1 milliamp. So this probe steps 1 whole amp down to 1 milliamp. So you would put this on milliamps, and for every amp that you read here around a motor lead, when you clamp it, it would say 1 milliamp. So if it was 10 milliamps, it would be 10 amps. Okay. So that attachment is what you can use on that meter for checking amps now. But that's not what we're doing right now. I'm just showing you what it'll do. So all that comes in your accessory kit if you get the whole thing. That comes with a Fluke 1587.
How much is that?
It's around $750 to get this. If you get the whole kit, probably around $900 or $1,000 to get all of it. If you get the amp clamp plus all the probes and a temperature probe and all, it's probably going to be just under $1,000, which is actually it is very much worth it.
We'll let Smith pay for that.
Now, you see that probe right there? That probe there has a button on it that you press to test it with. It's just one cable there, but it has a high voltage thing, and then these two little things is actually the button. You press the button, it actually makes those two right there together, and it tells the meter to shoot voltage up that line there. Okay, so it goes over to here. It goes in that special jack over there. So let's plug into that, and so it goes right in there like that on the left. That's where your high voltage probe goes. It produces voltage on this and shoots it into the motor. And then you take your common lead. This set also comes with alligator clips that can attach out, and you can put a regular probe in there. So if you're just using a probe, then you put the probe in there like that, and it's a probe. If you're going to do alligator clip, you pull the probe out and you go in there like with that, and then you have that. So this kit is very much worth having. Next thing, you put your common, you don't put it down here. You don't put it over here. You put it over here for minus on insulation. So if you're doing insulation, that's plus, and that's minus over there. You see that in orange?
Yeah.
So you have to go over here with your common to get an accurate test when you're doing insulation testing. You go to insulation, you choose your voltage, you're going to test that. Okay? And then you're ready. Now you can also hit that button there. This button will do the same thing as that button will. The little thumb button on the probe, I prefer doing this one. But if you would rather do this, you can. Okay, so it's the same thing as that. All right, so now let's go there, and let's check. I've also got See if I think I'm getting hung up with my camera. Yeah, I am. So we're going to go to ground on the motor here. Let me get out and move back. So you're seeing the motor and the meter, okay? And so now we're going to take, you see that clip there? The red one actually goes on that right there, on that stab there. So you go into here like that, and I can actually clip the motor lead. So I'm just going to go now to one. One is the blue wire, like that. So I'm going from one to ground right there. And, well, first of all, before you do anything, you separate the leads like that, keep them separated, and hit the test button and see what the meter says. Now watch. With the leads separated, and I hit the button, watch what it says. Now, what does it say? Greater than 550 million ohms. Greater than means it's actually above the meter can't read no higher than that. That's the maximum resistance. It can read 550 meg on this meter. Greater than means it's actually above that, which is effectively an open circuit, okay? It doesn't say OL, it just gives you, it says greater than the highest reading it can do. Now that's with it open, that's what it's supposed to be. It's supposed to be so high that it's beyond what it can read. Now, and then I let go, of course, it holds it on there. Now, the next step to test a meter is this. Short the wires together like this. Put them together like that. And you want to do a dead short circuit test and see, does this say 0? So you put them together and hit the button like this and watch. Look at that. What does that say? 0.0 megohms. Now that's a dead short in a motor. It could read that low. That's bad, okay? Because you don't want a connection between a hot wire and ground, right? What it's doing is it's detecting if you have any leakage current from the insulation in that wire, if it's cracked or melted inside the motor, it's going to tell you, is there any current leaking from this getting on the frame and coming back on that ground wire? It's detecting leakage current in there that's going to ground. So here we go. We're going to ground, and we're going to go to line 1. We have those two hooked up, and we go back to here, and I hit the test button, and it says, or I can, just for your sake, I can hit it up here and watch. Just watch it. See that? And what does it say?
550.
Greater than 550 meg, so it's actually good. Let's go to line 2. And you got to keep these leads separated. Don't let them hit each other, and don't touch them because it can light your world up if you touch them now. So you can know it. So hit the button. Greater than 550 meg, so that's considered. If you're over 1 meg, you're okay. Okay. Let's go to 3 and hit it. And it says greater than 550. Now let's take a look at a bad motor. Let's flip it around. So let's play musical motors here. I got this bad one was actually donated by Butterball. So what you're getting ready to see right now is one that they sent over here. They put my name on this motor. Okay. You see that tag right there? Senator Durwood King of the SCC. That come from the butterball plant, that bad one right there. So this is one that's actually fried. It come from their plant. So let's take a look inside of it. And now just to show you that you got, this is already hooked up, it's high voltage. You got 1, 1 and 2, and you've got 3 that are available. Okay, down in there, you've got 6 and 9. Okay, you've got 4 and 7, 4 and 7 together. And then you have 8, and you've got 5. See that? So 8 and 5 are together down the wiring up. There's your 5 and your 8. So it's configured for high voltage, and I've got a ground wire. So now let's go to line 1, and let's get the meter where you can see it. You raise up some. Go. Let's see. Now, trying to be where you can see the motor. I tell you what, I may just move the meter over this way. How about that? Let's go that way and go. That's better, ain't it?
Yeah.
Now, so let's go. Let's put our ground on, and then let's go to line 1. Now you look close at this here now. Ground in line 1, I'm going to hit my button to watch. What does it say?
Greater than 550.
Greater than 550. Let's go to line 2. See that?
Mm-hmm.
Line 2 is bad. So this meter picked that up. It picked it up that it's bad. But I average ohm meter, and I want to just show you just for the heck of it, that the average ohm meter usually won't pick that up unless it's actually a hard. If they can, but not guaranteed. So I'm just going to show you. Hold on. Give me just a second here.
Away.
Okay. Now, the meter, that's a meter that y'all use at the shop a lot of. Now, let me just give you a caution here. You see that right there? What does that say right there?
Let's see. 1K?
1K ohm. When you go to ohms, it won't read no higher than 1,000 ohms, okay? 1K. That's as high as it'll read. So if I go to ground, I go to ground, and then I also go to line 2 there. You see that? It ain't reading it, is it?
No.
It's not reading it because, look, this meter won't read above 1,000 ohms. This meter will read it in the millions of ohms. That's why this meter is no good for doing what we just did, because you'll think that motor's all right, but that motor's not all right, you know? See what I'm saying?
With that meter you got on, do it between the faces. See if you got a phase going up.
Say it again.
With that T5 1000, do it between the faces 1, 2, and 3, and see what you get.
Now, between the phases, you're going to read through the motor. Now, that's another subject. Now, let's hold that just for a second now. Just for a second. Okay, let's systematically let's systematically step through this now. You saw that phase 2 read 0.2 megohms, right? Now let's go to phase 3. Phase 3, now watch. It's reading 0. You see that? That's hardcore short. Now, so we're checking each leg to ground. Now, your other test, this tells you, do you have a winding shorted to ground? Okay. What it doesn't tell you is, do you have a broken winding, like an open winding that's actually broken in two inside the motor? So the way that you, if you look closely, look back on your screen here, what you're talking about, Victor, is this. So let's go back to a screen share. Go back to your screen share and look at here. When you put your ohm meter between T1 and T2, you're going to read through the windings and you're going to get a reading, okay? You're going to actually read the resistance of those 4 windings in series. If you read from 1 to 2 or 1 to 3, you're going to read through that set of windings. If you read from 2 to 3, you're going to read through those windings. It's going to give you the internal resistance of the motor, and it's going to tell you if all 3 readings are the same, like from here to here, here to here, and here to here. If you do those 3 resistance readings through the motor and they're fairly the same, that tells you that the windings are in the same condition, okay? Or they're healthy. If you have an open circuit from 1 to 3, but you get a good resistance from 1 to 2, you've actually got a broken winding in here somewhere or a wire nut has come off, okay? That makes sense?
Yes, sir.
Yeah.
So that the test that you're seeing, let's go ahead and do that. If we check through the motor, we should actually get a balanced resistance of ohms from 1 to 2, 1 to 3, and also 2 to 3. Okay, so let's try that on this one, and then let's try it on the good motor, and let's find out. Now, if you look closely over here on the lab sheet, what does it tell you, Victor, about the test here that you're talking about? At the bottom it says continuity testing for an open or a broken motor winding. You can use an ohm meter. You use an ohm meter for that. And you're going to check from T1 to T2, not the ground.
Yep.
And 1 to 3, and then 2 to 3. And all that's telling you is, do you have a broken winding, or are the windings starting to deteriorate and get a high resistance with internally? And larger motors are going to give you between 0 and 3 ohms. Smaller ones like this white one in here are going to actually be higher ohms, around 20 or 25 ohms. But they'll all be balanced readings between those 3 sets there. So when you get the 3 readings, they should be very, very similar. So let's go back to the camera, and let's check the bad motor, and we're going to go through the windings, not the ground. Okay. So another thing, look, when you go to the meter, here's what you got to do. You're not going to use that probe, and you're not going to shoot voltage into it. You're going to go back and use these with the regular leads. Okay. Now let me just show you what this meter does before we do that. What's actually being produced out of here, and this could really be an eye opener to you. And the way, if you want to see what this meter actually does, which will be a surprise to you. Let me get the current clamp out of the way. Get the current clamp out, and let's go back to now. So, you know, what we just did, we injected into the motor, it was actually high voltage, and I want you to see that on another meter here. So guess what we're going to do? We're going to let this meter tell you, this is going to tell you what that's doing. So watch. We're going to go to the volts here. The voltage right there, okay? I'm going to take the high voltage probe and shoot it right there, right into that other meter. I'm going to put the commons together. Okay. And now here's what you're going to see happen. It's when I hit that button there, this meter is going to tell you what the other one's putting out, because I've actually got them going head to head. You see that? I got them going lead to lead, face to face. This is face to face with that meg tester now. Now watch it close. What does that say?
524 DC.
524 volts DC that meg tester is producing. Now look, up here it says 521, you see? It's actually producing that much voltage, and this meter here is agreeing pretty close to it, 524, see it? So this thing ain't no joke, man. If you get your hands on that thing, you're gonna know it. You're gonna know it, okay? So you don't wanna touch it. So to check continuity through the motor, going through the windings, you can actually use that basic meter there to do it. You don't have to use this. If you use this, you got to switch over to the other probes and then change the setting to ohms, okay? So if you were going to do it on this one, you put it on ohms, and you got to put a probe in here and put one in there, okay? You switch over to here like that. And then you get out your other basic red probe and go into here. Take the clip off of that. And now you're just using the two basic probes here going into here and here, okay? And we're going to go 1, 1 and 2. And from 1 to 2, we've actually got an open circuit. You see there, OL? It's above 60 million ohms. 60 meg is the range on that resistance. OL, so it's beyond that. So that means that you have a broken winding in the motor, because you should actually be reading through that Y connection. If you look here, right now, you should be getting a resistance reading from here to here. Okay, you follow?
Yes, sir.
Yeah.
But you're not getting it. You're getting an open circuit inside that motor. That motor's actually got a broken winding or burned open on the inside. Now let's go 1 to 3. 1 to 3 is still open. How about 2 to 3? 2 to 3, you got extremely high resistance. You got 213 kilo ohms. If you look at that, that's kilo ohms. This motor is definitely no good. It's fried, okay? So, Victor, does that help seeing that?
Yes, sir.
So you had an extremely bad motor. That's why they tagged that thing, and they put on there to bring it to me at this school, because it's one of them motors. It's a classic that it is horribly bad. Let's flip it around and do a resistance reading through this one, and you'll see that this is a healthy motor over here. And it'll be obvious when you get the resistance readings that they will be balanced, that it's a healthy motor. So let's flip this around.
I got a dumb question.
All right, go ahead.
So what if like one of your maybe your T1 and T2 is higher than the other one?
Okay, then what that means is that your windings are not matched anymore, and you can look out. That motor is on the way out.
On the way out?
Yeah,
All right.
motor's on the way out, buddy. On the way out, man. If they're not really close to each other, you can. Here's what you do. You want to keep a log every couple of weeks. You want to do an amp check per leg, a PM, and record that on larger motors that are critical. Do that every so often. And if you see a change in amps, you could also do a meg test on larger motors every so often, and a resistance test like we're looking at doing right here. When you do a resistance test through the windings, and you check through them, And let's say that this month you get a resistance reading of 20 ohms in every direction here, 20 and 20 and 20. But next month you see 20 and 30 and 20. Something's wrong. The next month you get 20 and 40 and 20. So guess what? Something's happening down in here. You need to check your wire nut that's in here and make sure it's okay, because your wire nut may be an issue. You may have corrosion in there, or you may have oxidation in that wire nut causing that resistance to be high. If it's not, if you take it apart and redo it, and you still have a high resistance going this way, but balance readings that way, there's something going on. Them windings are on the way out, and you can sure look for a trend of the resistance getting higher as time goes along, and you're going to see that motor eventually go bad. That makes sense?
PM for Christian.
That's where your PMs come in, and you want to keep a record of what the resistance is every time you check it. If you see a trend of it changing and going higher, you better be ordering a motor. You better be getting a motor on the shelf quick, because when it starts changing, you don't know if it's going to be slow or quick change. You know what I mean?
Yeah.
And if it's a big 150 horse motor, you better be finding a source for one, because they're not real, they're not so fast to get necessarily. So anyhow, so now let's take the leads now, and let's see where they're at. So you can also check here. You put these together, put them together, and make sure it reads less than 1. That's 0.2 ohms. You see that? It's 0.2 ohms. So you want to make sure that your test leads are good before you do any of this. You're going to make sure the meter's right and that the test resistance of the leads is very, very low like this. Not K ohms, but actually ohms. Okay, now, so we know that's fine. And when you take it apart, it says, oh, well, so the meter and the leads are good. Don't let a bad meter make you think you got a bad motor and change the motor for no reason. So now we're going to go from 1 to 2. So 1 to 2 is reading what?
21.
21.
Well, how do we know if we walk, maybe we have a bad motor? How do we know we're supposed to get that number? Is there something on that motor tag we got to do? Like
no, it doesn't tell you what it's supposed to be. You'd have to compare it to another motor that's like it.
Okay.
They don't tell you what the ohms would be. I've never seen that included on a motor anywhere. But if you got another one like that in the plant, then you need to quickly check one that actually works right. But the rule of thumb is this: the larger the motor, the less that's going to be. Like really larger motors, if you get around 10 horse and up, that number is going to be way down close to 0. It may even be like less than 1 ohm. And the smaller the motor, the smaller the wire, and the higher the resistance, because the windings inside the motor are really small, and so they have more resistance to them when they're real tiny fine wire, So cool. It all boils down to the size, the gauge of the wire inside the motor is going to be small in here.
We kind of go by that. The lower the horsepower, higher the.
Yes, sir. Absolutely. So now you went 1 to 2. All right, now let's go 1 to 3. Now keep a note, they all should be close to 21, okay? So that was 1 to 2. Now 1 to 3. 20.9. See that? And now let's go 2 to 3. 20.9. So those windings are what you would consider to be healthy. Those windings are balanced. They're all in the same condition, and that's reasonable for a small motor. That's a 3/4 horse motor there. That's not even a whole horse. It's a 0.75 horse. So that's okay. That's okay for that. Now, if it was a 5 horse, you could look for it to be way less than that. If it was a 10 horse, even less. I've seen some large motors that the resistance was way down around 1 ohm, or maybe slightly less than 1, because the windings were so large that there's very little resistance in there. They conduct so good that the ohms is very low. So those are your those are your tests there that can tell you. You know, you go through the meg test with high voltage from each leg to ground, and you do your continuity test through the windings to tell you if you have a broken winding. Now, let me just tell you, in my whole life now, I was in the last plant I was in for 20 solid years. Now, listen now, I saw one motor in 20 years that actually had a broken winding. And here's what happened. Here's what happened. This is a true story. This motor was actually kind of, it was turning, but it was turning kind of like this right here. You could actually see it turning. And it had a noise to it. It was going like, whoa, 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 and it was turning, but it had a sound to it that wasn't right. Okay, it was slow. It almost sounded like it was single phasing, and it actually was. But here's the bad thing now. Here's what blows my mind. Is I had voltage on all three legs. It wasn't missing voltage going to the motor. All the legs were actually there when I checked them to ground or phase to phase. The motor had the right voltage going to it. But guess what? It was single phasing internally because it had a broke winding on the inside. So here's what it was, man. You go up here and you check the amps on one leg, and you would be drawing amps. The next leg you're drawing amps, and the next leg ain't drawing no amps. So you had amps, and no amps. Okay, and you had higher amps on two legs and no amps on the third leg. So your amps, so if you got a broken winding in there, what you're going to have is an imbalance on current. You're going to have, it's not going to be the same amps per leg when you check those three, you know. You check them all, and they're not going to be similar. They're going to be, two of them that'll be similar, higher than normal, and the other one won't have anything. So that actually blew my mind. I had never seen that in my life, and it had me. It was in one of them moments that it was a curveball to me, and I didn't know I didn't know what I was looking at, and it kind of had me tripping there, guys. I swear it did, because it was a recirculating fan for an oven. It was real hot back there, about 115 degrees. I'm sweating bullets, and I didn't know what I was looking at. I said, man, how do I reason this out? I got all the voltage there like I'm supposed to, but yet I got amps, and no amps. And the motor is sitting there crawling, and it's a groaning. And I said, so after I thought about it a while, I did a meg test on the motor, and the motor did not read bad to ground. Okay, so listen, when you check each leg to ground with a meg tester, it did not read bad. So I said, the first thing I said was, it ain't reading bad with the meg test, so the motor must not be bad. That was my mistake, because look, insulation is not the only thing that can go bad. They can be shorted to ground, but that one was not shorted to ground. It actually had a broke winding. So it had a broke winding in here, causing it to single phase internally in the motor and drawing amps, and no amps. So you see what I'm saying?
Yeah.
That's where this test comes in. That this is going to tell you that rare cases that you see this. It's very rare. I saw one in 20 years. I'm telling you, no kidding, one. But that one made me. It had me. I honestly, I swear, I didn't know what I was looking at. I did not know what I was looking at. I said, my gosh, what in the world what is this? I said, the only thing I ever knew about checking that I ever did on them was check them the ground. But then I got to thinking, I need maybe just check through the motor, and I did that, and that's where it showed up. That's where it showed up when you check resistance through the motor. That's where it showed up that it was that it had an open leg. And what do you think about that?
I think like 2 or 3 that lost the face.
What now?
I seen like 2 or 3 that has lost the face.
Yeah, inside the motor.
Yeah.
Yes, sir.
So you checked it with the meter with your ohms, and one of the faces won't give you nothing.
Exactly. That's exactly what we were like what we saw a while ago with that bad motor back in here. You know, that's what we saw.
Yeah.
Is when you check through it, you actually had a winding broke open, not shorted to ground now, but just broke open.
Kind of like a rule of thumb, like you go in there if you got something going on, go ahead and get that out of the way.
Right. Right. You can, if you wanted to do this test first, you could. It all depends on the symptoms.
Yeah.
It all depends. It actually depends on the symptoms of the motor. If the motor is sitting there, if it's just a crawling and it's making a single phase and groaning noise like a or just humming, but all of the voltages are there. You know, all of the voltages are there. You know, that's an indication that you may have an open winding. If you check each lead to ground and then check phase to phase, and all the voltages are there, but yet the motor doesn't behave right, then you want to check through them, check an internal resistance that way, and that's gonna tell you if you have this. So, guys, if I were you, I would take what I emailed y'all, these sheets here, and put them on your computer, put them on your smartphone, share them with other people, maybe make some hard copies. I got these on the 11 by 17 paper. That's like 2 pieces of notebook paper. If you can get somebody in your office to print you some of them, get your secretary to print them, put them in your toolbox, and you'll have them, and share them with people. The other one I sent you is actually on Delta. It's on Delta. Now, one thing about Delta, and once I say that, I'm going to close because I know it's getting late. The Delta sheet does the same test right here, okay? Now, what I would do is I would wire the Delta on high voltage. And when you do that, you're going to test 1, 2, and 3 to ground. You're going to put 4 and 7 together, 5 and 8, and 6 and 9, which would be here. You got 5 and 8, 4 and 7, 6 and 9. You put wire nuts in there, and it gives you a series delta. All these are in series, and it forms a single delta, one delta, okay? And then, so you check each lead to ground with your insulation tester like we just did, and that's how you check a delta motor doing it on high voltage.
But that's all the, excuse my ignorant question, but that's all the Mega does, insulation?
Say it again.
That's all the Mega does, insulation test?
Well, no, Lord, no. Look, this meter here, look, it does insulation, it does milliamps, it does milliamps AC. In the blue, look, if I go here, it does AC milliamps. In the blue, if I hit the blue button, then it does DC milliamps. You see that?
Mm-hmm.
DC milliamps, AC milliamps. And the milliamps is used with that current clamp. Okay?
Yeah, but you know they just like sell separate like insulation, Mega insulation meters.
Sure, yeah. Like you know, the this one. You know, this one here. The crank type. Like that. That one right there. That one right there does insulation. It'll also do voltage testing, but I said it won't do anything else. But that's the old kind that actually generates it. What I hand wound generator. Okay. So if you were interested in seeing that, I could show you. But basically, these are your 2 leads. That's what you would test a motor with. You hook a lead from this to the actual ground, and then that's what you're going to check. Also, but that's going to be. This is actually a ground for the instrument itself. So the actual metal parts of this, you want to actually ground those to the motor also, and then you're going to use here your ground and your hot for checking to doing the test the same way we just did a while ago. And it tells you, if you look over here, the minimum reading is actually 1 megohm right here. You see it 1?
Yeah.
So 1, when it swings way over and it pegs, it's bad, okay? If it stays way over to the left, you know, way up in the high megohms, then you're fine. Yeah, I can show you on a bad one. If you do you want to see that one or?
I don't know about the guys. Well, what do y'all think?
It's up to you. It's your time. I can show you. It won't take. I can flip the bad one around and show you how bad one reads. I'll show you how a good one reads. If you're in, if not, I'll leave it alone. Basically, when you crank it, if it swings way over, it's bad. Okay, that's all. If it stays over there, you're fine. Up here, you're way up in the high mega ohms. So if you're over 1, you're fine. That meter tells you if you're over 1, if you're in that range in there, you're okay. If it swings over hard, way over to here, it's bad.
No.
Okay. So that's basically it. If you don't have one of those at the plant, do you? Don't you have the digital kind?
Yeah. They bought us one, the digital kind. It's kind of the same principle you got there. But
Right.
It's kind of looks like.
Like this. This is the digital kind. This is better right here because it does so much more. That one, if you look, man, look at all the other stuff that it does. Look, it does the amps. It does continuity checking like beeper. Oh, I better get them leads apart. It does a ringer test like continuity. It checks diodes in the blue. The blue function is diode testing. This is ohms. In the blue, it's a capacitor check. If I hit this, then it turns into farads. It checks capacitors. Capacitors are on single phase motors to give them actually a booster. You can take a capacitor out of a single phase motor and check it here on the blue function, and it'll tell you the microfarad reading in here. Okay, it does millivolts. It does temperature readings in the blue. It does DC voltage. It does AC voltage, and then in the blue it does low pass voltage for VFD. So if you have a VFD output, you put it on AC volts and you hit the blue button. And what it does is it filters out harmonics that can confuse a meter. This is a true RMS meter that can read the output of a VFD very accurately. I'll show you Thursday night how if you use this function that says low pass, the blue, if you put it on AC volts and hit the blue button, it's going to be low pass. And what it does is it actually blocks harmonics out of the meter that can confuse it that a VFD produces. So I'll show you how this works with a VFD Thursday night, checking the output to the motor, and also an oscilloscope that actually shows you the wave on a VFD. So try hard to be here Thursday, and I'll show you how to do VFD testing on the outputs with this meter plus a digital scope that's a handheld scope that draws the waveforms on there. And you can see what the waveform looks like leaving the VFD at different frequencies, okay? So now, the only other thing that I'll mention now, and this will be enough in closing, would be this. If you had a Delta motor doing at high voltage, it's the same numbering as a Y, okay? It's the same actual numbering. If you look, if you compare, it's 4 and 7 and 5 and 8 and 6 and 9 if it's high, okay? Which puts them in series, which is like this, 4 and 7, 5, 8, 6 and 9. It makes them in series whether it's a Y or Delta. Low voltage Delta, when you're doing it at 230 or 240, look at here. This is the one that's so different from anything else. You take your incoming line coming from the starter, and the starter feeds and it connects with 1, 6, and 7 at the same time. So there's actually 4 wires together here in the CAD head for that line. Line 2 from the starter, it comes and it meets with 2, 4, and 8. You get 4 wires here, including the incoming. Line 3 comes in, it hits 3, 5, and 9. You see that? Mm-hmm. Now, if you watch closely, it forms a double delta on low voltage. And here's how that works. And then this will be the end. This will be the end of my talking tonight. If you look at here, the incoming T1 hits 1, 6, and 7. Now watch here. It hits 1, it hits 6 and 7. It hits the top wire here, the top one there, and the top one there. You see it?
Yeah.
And then the second line hits 2, 4, and 8. So line 2 comes in, and then it hits 2 and 4 and 8. So it hits the bottom right of each set. 2, 4, the same phase, the same T2 phase hits 2, 4, and 8, and they're together, okay? And then the third leg coming in, it hits 3, 5, and 9 coming from the starter. So T3 comes in, hits 3, it hits 5, and it hits 9. So it hits the lower left here, lower left, and lower left. Now, what that does, that's hard to picture that, but it forms actually 2 deltas, and I'm going to show you a picture. Watch the screen. Watch the screen real closely. This is going to be my last screen here. This, I go share screen, and I'm going to pull up something that shows you that it's actually double delta. So that is single delta on high voltage there. Now here's what double delta looks like. If I go documents here and go down. This is one I had to look for to find this because I couldn't picture what was going on until I found this. So labs. Now you look at this right here. And you might want to take a picture with your phone of this because this is one that's not real common to see. You see that? Now, if you look at here, it's got 1, 6, and 7 together. You see that? Now, if you go here on the paper, what do you see here? 1, 6, and 7. You see that? And then down here, you've got 2, 4, and 8 together. All right, look here on the paper. 2, 4, and 8. See that with a wire nut? With the incoming wire, so there's 4 wires per. And then this corner is 3, 5, and 9 that actually go together. So here you've got 3, 5, and 9. You see that?
Mm-hmm.
So when you have a delta motor that's wired low voltage like on 240, it's not 1 delta series, it's actually 2 deltas in parallel. It's like this. You see that? You have a delta in the center and you have a delta on the outside, and they're in parallel. That makes sense?
Yeah.
So that's something there that I searched the internet to find that, and whoever did that did a fine job. I actually tried to do it myself on paper. I got myself screwed up trying to draw it, you know. But I found that, and this actually shows you, you know, that's what it is. Now, if you go, let me tell you something to go look at, and in closing, here's what you can do. You see that nameplate right there?
Yeah.
Now, when you go back to the school, when the school opens up, I want you guys to go down to the welding shop, and you go behind the old welding shop, and you look at the air compressor back there behind under the shelter that runs the whole welding shop. And you look on that motor down there that we wired up, and that motor tells you, it says delta wound, and at the bottom of it, it shows 2 triangles. It shows a double delta triangle set up, stamped on that nameplate, 2 triangles side by side, and it says delta wound. Now, when we installed that compressor down there, me and my class did about a year, well, close to 2 years ago. It had to be wired 243 phase, and it came in already pre-wired that way. We just tied the main power in, and when I saw that on the nameplate, I took pictures of it, and I'm trying to remember. I don't know right where they are on my computer, whether I've even got them in this computer or not. But let's see. But you saw what I just showed you, and that shows you that it actually is. It's actually two deltas in parallel when you go low voltage, and it's one delta when it's in series. Now, some motors actually have 12 wires to them, not 9. And what they'll do, guys, is this. They'll actually have a 12 lead motor like at Schindler. Jameson, where you're at, you can ask them guys about their 12 lead Y delta motors. And what they'll do is they'll have, this won't be connected inside. This won't be connected inside to where if you got a delta, these are already pre-connected inside. If you get a 12 lead motor, none of these windings are hooked together. You've actually got a bunch of separate windings like this. There's no Y and there's no delta. And what you do is you take the 12 wires that come out of the motor and you go to a double starter. And that double starter configures it like this on startup for a soft start, because that gives a soft start there. And then when you get up close to top speed, that contactor kicks out and the other one kicks in, and it changes the wiring to this for that motor externally outside the motor. So it's called a Y start delta run. And that one motor runs Y on startup, and it switches to delta after it goes over the startup period and does a soft start. It goes into this to get higher torque. So have y'all ever heard of that, a Y start delta run?
No.
Okay. In our book, if you go to I'm going to flip real quick, and you can look. We can talk about it some Thursday. We actually talked about it the other day.
Yeah, I remember you talking about it.
Yeah, it actually in our book. If you go in our book, I'll show you that if you ever have any dealings with it, I'll just say that. If you ever do, here's where it is. It's right over here. It says Y delta starting. You see that?
Mm-hmm.
It says Y delta starting right there, page 247.
Yep.
So I'll just flip real quick to it. So there it is right there. This is your book here, chapter 26, Y delta starting. And they get into some pretty serious math in here. And they're showing you startup amps on delta, which is going to be high amps. If you look over here, startup amps of Y is less. So if you wire a motor Y, it has lower startup amps, and it actually has a softer start than delta. So what they'll do is externally, they'll actually change the configuration of the motor to where nothing's wired internally in the motor. They do all of it with a double starter with two starters, and one of them does a Y start, and the other one does delta run. So it's kind of like looking at a reversing starter with two sides to it, but you have a Y side and a delta side, and you have it starts out in this configuration with low amps, so you don't have high end rush. You get a soft start characteristic, and also there goes your there's your Y configuration, and then there goes your delta. So they're actually doing this external from the motor. They're doing it with a control circuit that actually changes the internal pattern of the motor outside the motor. And that's what Schindler's doing on their escalators. They're actually doing this when they don't use a VFD. So if you on smaller motors that are below 5 kilowatt, I believe, I think if they're below 5,000 watt motor, it's in kilowatts there, then they're doing this. If you get really big ones, then they go with a standard delta motor, and they use a VFD to give you a soft start. They program a VFD to give you a soft start. So, but again, you can if you ever need to get into it, it's in this book. I'll try to touch on it Thursday night a little bit, This book actually could cover another whole semester, guys. There is so much more in this book that I wish we could go over. It gets into actually brake motors that have brakes on them, mechanical brakes. It's got, you know, we could do another whole semester, man. I swear we could. Solid state controls. There's just, you know, there's just not enough time, you know, to cover so much. But keep in mind, anything down the road you get into, if you want some help with it, you can always get up with me even after the class is done a year or two from now. I mean, I'm always interested in helping people. So if you run into something that's more advanced than what we covered, you can always get up with me, man. I'll try to help you with it. And even if I don't know the answer, I guarantee you, I bet you $5 I can get an answer. Because, man, I got connections with people that are as smart as you're going to find. I'm serious. I mean, I've got connection with Rockwell. I got phone, Victor, you got numbers for Rockwell. I mean, I know people, I got people I can call that can answer about anything you could ask. I mean, seriously, it's if I don't know it, I know somebody that does. So, I do want to help you guys beyond the class. If you need it, I would be glad to. So, I'm gonna get this here because it is getting late. I've run over. But the only reason I did, guys, is because this is the next to last night. Thursday night will be it, and then the exam is going to be Tuesday. So for the exam, basically what you'll do is I'll have questions in there in Moodle, and what I'm going to do is I'm going to put a reference beside the question of what chapter the answer is going to be in. And you can do it kind of like a state electrical test. You just do it open book. Don't even worry about it. So it's because we don't have time to review. It's going to be based on the worksheets that you've already done. So the questions are going to come from your worksheets. You can actually print your worksheets out of Moodle. You can actually, when you go back in there, and I would advise you doing it, if you don't print them, then you can actually save them to your hard drive. So you can go in there, and when you pull up your worksheet that's been graded, you can actually print it, or you can just save it. You can do a save to your hard drive, and but I honestly would print them, because once you get beyond this class, I'm not sure if you do. I don't know that you would actually be able to pull it up and read it once you get out of Moodle. You probably wouldn't. But I haven't actually looked into that of trying to view it outside of Moodle. I don't know if you can or can't. But I do know if you print them on a hard copy, it's yours. It's yours permanently, you know, because, again, once you get past this semester, you're not going to be able to get in there. Those worksheets are going to be gone. What you've done is going to be gone. So I would advise saving everything you have. That's a bad thing I don't like about this electronic stuff is that if you don't save it and print it, it's going to be gone after this semester. That just makes me feel bad. You know what I mean? I like to have I still got notebooks of all my notes, man, from 1984 and 86 when I took electronics. I've got every note I ever took in notebooks. I still got them in my house. So I haven't thrown any of that stuff away because electrical theory does not change. It hasn't changed since George Simon Ohm come up with Ohm's law, and it ain't going to change. So, you know, so your work really is worth saving for sure. If you're interested in doing that, try it. And if you hit a snag with trying to print it out, let me know and I'll try to help you. But you should be able to figure it out pretty easy. So but anyway, so we'll go ahead and close, and I hope you guys can join Thursday. We're going to focus on VFDs. I'll have a VFD out here on the board, hooked to that good motor there, and we're going to go over some programming things and mainly on measurements with a meter, with that fluke meter, doing measurements, and also with the oscilloscope. So that's something that not many people get into doing, but it's a very good thing to do, and I'm going to just show you some reasons why it's good to know what to do when you're dealing with the output of VFD. So the signals are way different than a sine wave. It's not a sine wave coming out of, it's like a square wave. It's kind of chopped up square wave looking thing. So, but once you see what the wave should look like, it'll help you to determine whether the VFD is putting out right or not. So, okay, guys, and thank you for joining. Y'all make it worth it. You really do. You're the reason I'm into this. Is to try to help people, and it's a good feeling when people stick around. When people don't come, it's just, I guess some of them think never use. They've already got in mind maybe a different route that they're going to go instead of industrial. And that's okay, because everybody's got a path that they can get on. So, right, well, you guys have a good night, man. Thank you.
Have a good one.
Have a blessed evening. Hope to see you Thursday.
Okay.
And I did record, so once I end it, I'm going to be checking for the. They'll send me a notification when I can actually send a link to y'all, to everybody, and people could watch. So have a good night. Thank you.
All right, thank you.
Have a blessed night.